Hello? Yeah. Works.
Okay, good morning, everyone, and welcome to the second week of the Simple School. So we are the first speaker of today is Carlos Amendola, and Carlos will continue uh, from where he left. And I hope you are having great time in Lahore in the pleasant weather of the city. And please stay motivated. And because in this week we have some new lectures, some new topics, some more interesting discussion around the same subject what we started last week, and we are going to continue the same with Carlos. इसको इसको रिमूव करें प्लीज यहाँ से ये दोनों चीजों को उठा लें इसको भी आगे करते हैं क्योंकि वो बोर्ड यूज होना है इसका तो नहीं ये नहीं हिल सकता ये टेबल हाँ थोड़ा सा आगे तो हो सकता है कि थोड़ा आगे हो सकता है टोटली फिक्स है ये वाली चीज पैनल इसके लगा हुआ है इसकी केबलिंग वगैरह मिल जाएगा थोड़ा सा यार आई थिंक इतनी होगी इसको भी उठा रहे हैं क्योंकि वरना ये तारों नहीं है इसको भी उठा
Yeah. Okay.
इसको उधर
Yeah. All right. Then I will start. And so first, where were we? So if you remember, my lecture was about linear Gaussian graphical models. So first I'm gonna recall. We had a directed graph. With m vertices. And then we defined a recursive linear model of the form x equals lambda transpose times x plus epsilon. And here, lambda belongs to the set Re, which we defined as all the matrices m by m, such that lambda ij, the entry ij is 0 if there is no edge that goes from I to j. Okay. And so, well, remember, so this just means that the pair I comma j is not in D, right? It's not in this directed part. All right, and so that was the lambda, and the epsilon was a multivariate Gaussian with mean 0 and covariance matrix omega, and omega is a diagonal matrix like this. That's of course has to be positive definite, and I'm gonna denote this like this: PDM diag, because like positive definite matrices m by m that are diagonal. Question? Yes. Oh, thank you. I'm again thinking of edges. Thanks. D. Lambda and RD. And very good. So that was the setup, and from there we define then the linear Gaussian graphical model associated to G right, as well is all multivariate Gaussians M sigma such that the sigma is in what we call Mg, and Mg was the parameterization of the covariance matrices. So that would be identity minus lambda minus transpose times omega times identity minus lambda inverse. And then here lambda is in D reg, and omega is in PDM diagonal. Okay, so this is just recalling. And maybe I'll just recall here what the RD reg was. And so that's all lambdas in RD such that the determinant of 1 minus lambda is not 0. Okay, so all the ones that are actually invertible in RD. All right, so this is the setup we had. So it was just recalling the main definitions we had. And well, we actually observed one more thing, which is that if G is a DAG, right, so directed acyclic graph, then lambda can be chosen upper triangular. And in this case, then the RD reg equals the original, just RD. Okay. And that's because in this case, we have that the determinant of identity minus lambda is 1, which is, of course, different from 0. Okay. All right. So now what I want to tell you is first, the algebraic structure. I'm not sure if this is working yet. Oh, yes, working. Okay, so the algebraic structure is phi g. I'm gonna call this the map. So let's denote phi g to be RD reg. And so I choose one lambda and one omega. And this goes to positive definite matrices. So this map, so phi g lambda omega sends to identity minus lambda inverse, transpose identity minus lambda inverse. So this map is a rational map. In the parameters lambda ij and omega I. Yes.
What does phi lambda right transpose?
Here?
Yes, yes.
So just the inverse and transpose of the
Inverse
matrix,
and transpose. Okay.
or transpose and inverse.
Yeah.
Yes. So what I want to claim, so these are rational map. So why? Well, that's because when we take inverses, transpose, and multiply, everything is just a rational function, right? So a rational function is a polynomial divided by a polynomial, right? So the inverse of a matrix you can write explicitly as rational functions of the entries. And all the entries are just polynomials in lambda and omega, right? So that means we have something nice, something algebraic. So what does this mean? This means that MG is a nice same algebraic set. Right? So it's not just any set or subset of the cone of positive definite matrices. It's actually what we call same algebraic. And so this would be a consequence of the famous Tarski-Seidenberg theorem. Right, because we start with some same algebraic set, and we're having an image of this same algebraic set, which is a projection of the graph. And so same algebraic just means that, so it's the next best thing that we have, right, as an algebraic variety. So an algebraic variety is defined by polynomial equations. A same algebraic set is defined by polynomial equations and polynomial inequalities, right? So we also allow for inequalities, which is important for us, right? When we're looking at the statistical interpretation of these parameters. Okay, but okay, this is just that's the essence. This algebraic essence is clearly here. And well, we had a few examples in the tutorials. Let me, maybe I'm gonna recall one of them. The one that we did already. We have this example with the path. So we have just 1 goes to 2, 2 goes to 3. So in that case, well, identity minus lambda inverse was of this form. And the MG, or maybe instead of writing MG, I'm going to use now the notation I just introduced, which is phi. So phi G lambda omega, it's of this form, is omega 1, lambda 1, 2, omega 1, lambda 1, 2, lambda 2, 3, omega 1. And since it's a symmetric matrix, I'm just gonna write the upper triangular part. So this will be lambda 1, 2 squared, omega 1 plus omega 2, lambda 1, 2 squared, lambda 2, 3, omega 1. Okay, maybe I'm gonna need a bit more space here. And I hope you can see. Yeah, okay, I'm going to. Lambda 2, 3, omega 2. And the last entry, I'm gonna write here, lambda 1, 2 squared, lambda 2, 3 squared, omega 1, plus lambda 2, 3, omega 2 squared, plus omega 3. Okay, so the reason I write this explicitly is because one of my goals for today is that we will understand precisely each entry of this matrix and why does it look like this, each one of these entries. And so, well, the first thing we observe is that this map, it is true that it's a rational map, but it's actually better than rational. It's a polynomial map, right? And so let me then make that observation. And so the observation is that if G is a DAG, then phi G is polynomial. And well, why is this true? I guess I could have put this here, but So why is that true? Well, that's because if we look at this identity minus lambda inverse, right? So identity minus lambda inverse, if I think of this as this expansion, well, in that case, so if lambda is upper triangular with zeros on the diagonal, then that means that this matrix is nilpotent. Okay, so that means that there exists a point when I raise it to a power and then it just becomes a zero matrix. Right? And in this case, we actually can tell what power is sufficient. Which one would it be? Sorry? Well, in this specific example is 3. I agree. If we were in the general case where we have m, then m. Yes. And well, one way to see this is that, so you know, the lambda, I didn't write lambda here. I could have. Right, so lambda has a lambda 1, 2 here and a lambda 2, 3. But otherwise it's just zeros, right? And so lambda squared is gonna kill this part. There's gonna be one thing left, and then lambda cubed is already 0, right? So lambda squared, I mean, if I'm right, I think there should be a unique entry here, right? Lambda 1, 2, lambda 2, 3. And everything else is 0. Lambda 1, 2, lambda 2, 3. And so, yeah, so that means the lambda to the m is 0. And so, another way of seeing it is that the characteristic polynomial of such lambda is going to be lambda to the m, right? Because you have identity minus lambda, and then you get this, yeah, minus lambda to the m, right? So then when you use Cayley-Hamilton theorem, you'll see that lambda to the m has to be 0. Okay, and so this is good because that means that I can write explicitly the inverse of identity minus lambda. Lambda to the m minus 1. And then I'm just multiplying. When you do lambda to raise to some power, it's again a polynomial, and everything becomes polynomial in phi g. Okay? And so that is why now this shouldn't be a surprise that we obtained this. But even better, what can we say about these lambdas? What are we doing when we raise lambda to a power? Well, observe that it's lambda squared. What happened? There were zeros, and then in the entry 1, 3, I actually had lambda 1, 2 times lambda 2, 3, which corresponds to the path that goes from 1 to 3. So, and in general, note that lambda squared n3ij, right? So by definition, this is going to be the sum, k goes from 1 to m, of lambdas ik times lambda kj. Right? And so this means we are looking at paths of length 2. That, so you have a node I, a node j, and a node k that's in between. And this would correspond to having an edge I to k, and this an edge k to j. And so, Yeah, so this is like paths, directed paths of length 2. And well, by induction, you can convince yourselves that in general, lambda to the, what should I call it? To the L ij is encoding directed paths of length L. Okay, so it's a sum over different monomials, each one multiplying the weights along a directed path of length L. So let me make that explicit. So for a directed path, which I'm gonna call pi, and so it's gonna be I0 goes to I1, goes to I2, all the way to IL. And so this has a weight lambda I0, I1, lambda I1, I2, etc., up to lambda IL minus 1 IL. Sorry if it's a bit small, but it's just the weights from the from the path. And so, okay, so for a directed path, we let lambda pi be just the product of these weights. Okay, so we call this the path monomial. Because if we think of these as being the lambdas as variables, right, in a polynomial ring, then this would be a monomial. And the degree of this monomial will be L, right? And so, okay, so if we have this, let here, and let Pij, so this by definition is going to be the set of all directed paths from I to J. Okay, so with all of these notation, now we're ready to explain identity minus lambda inverse. Right, and what will that be? Well, the entries are certainly gonna be sums over path monomials corresponding to all the paths in the graph from I to J. And by the way I explained it, I hope then this is clear and doesn't need a proof, right? So so then I'm gonna say just we see then that identity minus lambda inverse entry ij is going to be the sum over pi's in Pij of lambda pi. Okay, and so then we have a combinatorial interpretation for the entry ij of identity minus lambda inverse. So that's very nice. And well, here it's a very small example, but there were many examples in the tutorial session. So if you did those, then you had some bigger entries, and then you can see what's happening. Maybe I'm gonna do a couple to see what we got here. So I don't know, maybe, okay, this one is very very short. There is only one path here, but you could have multiple paths. For example, we had this directed cycle was one of the examples we had. And there, the identity minus lambda inverse. So now we can just write without having to compute the whole inverse, right? This is great. So we can just write, okay, this will be gonna be 1, 1, 1, 1. This is gonna be zeros. And then here gonna have lambda 1, 2, because there is a unique path that goes from 1 to 2. Luring directed path is lambda 1, 2. There's gonna be lambda 1, 3. Here, this is where it gets interesting, right? The 1 to 4, there are two paths. There's the one going through 2, and the one going through 3. Okay, I'm gonna write like this. Okay, and then lambda 2, 3, what should it be? 0. Right? Because there are no directed paths that go from 2 to 3. So that will be a 0. And then from 2 to 4, there is lambda 2, 4. And finally, 3 to 4, lambda 3, 4. So this would be the matrix for that particular graph. And so here we observe two things. The first one was that if the Pij is empty, so there is no directed path from I to j, then, well, the corresponding entry is going to be 0, right? Because it's an empty sum here, right? It's an empty sum. But the other interesting thing that we can observe is that if I equals j in the diagonal, then we are getting, it's not 0, it's 1. And this is corresponding to the path of length 0. The one that doesn't need any edges, because you are already at the node, at the vertex I, right? So it corresponds to the path where you are at I and then you don't move. And so that's a directed path of length 0, and that's why the path monomial corresponding to that path is just 1. And then we add it, and that's the one that appears there. Okay, so maybe one more example. And as I said, so for the full list, I point back to the tutorial. And so maybe I'm gonna give you, in case you didn't do it, so I'm gonna give you a couple of minutes to fill out this matrix using that rule while I erase. And then I'm gonna ask you what the entries are. Okay, so let's see. So someone is already telling me. Okay, so this should be a 4x4 matrix, upper triangular, right? So, okay, so I'm gonna write, should I start with 1? I should start with 1, right? So I'm gonna do 1. Let me try to Okay, I don't know how, well, I actually do know how much space do I need. Okay, 0, 0, then 1, 0, and then maybe 1. Hopefully that's enough. Okay, so what's the entry here? Lambda 1, 2. Okay. What about this entry? So 1, 3. 1, 2, 2, 3. Correct. What about this one? The 2, 3 entry.
1, 2, 2, 3, 4.
Lambda 2, 3, right? And now maybe you were telling me this, the last one, right? Okay, what's this big one?
1, 2, lambda 2, 3.
Yes. Lambda 1.
1, 3, 3, 4.
So 1, 2, 2, 3, 3, 4.
1, 3, 3, 4.
And 1, 3, 3, 4, right? Okay, and then this one, 2, 3, 3, 4. And then there's another one here, which will be just lambda 3, 4, and then 1. All right. Very good. So now you're all experts on computing identity minus lambda inverse. I want to say, so what happens? I do want to talk about this case. If we don't have a DAG, can we still use this interpretation somehow? And so let's do it for the simplest case here. Well, it's actually, there will be a simplest case, which will be only just 2 nodes, but let me do it with 3 so that you can see what's happening. And well, in this case, well, we didn't compute, well, you could compute identity minus lambda inverse, but in this case, what happens is that this expression here is not finite anymore, right? And so if we look at the entry, let's say entry 1, 2. So if we just follow that, if you just believe that's true, right? So what would be the entry 1, 2? Well, there is the path lambda 1, 2. Let's go here. Lambda 1, 2, lambda 2, 3, lambda 3, 1. But now there are more directed paths, right? So there's none of length 2 or length 3, but there's one of length 4, which would be lambda 1, 2 times lambda 2, 3, lambda 3, 1, lambda 1, 2. And then there's another one, which would be lambda 1, 2, lambda 2, 3, lambda 3, 1, lambda 1, 2, squared. Like this. I think that's correct. And so I can actually factor a lambda 1, 2, and I get this interesting series, right? So I get lambda 2, 3, lambda 3, 1, lambda 1, 2, lambda 2, 3, lambda 3, 1, lambda 1, 2 squared, then cubed, etc. And so then it shouldn't be a surprise when it turns out this entry is actually this quantity. Okay, so if you compute the entry 1, 2 of identity minus lambda inverse, it's this rational expression, right? So remember we said it's a rational map, it has to be a rational expression. Well, it's this expression, and now we see the combinatorial interpretation kicking in here, right? So basically it's encoding all the paths, but you need to go around, right? So it's like goes around, and every time it goes around, it's a new loop that adds a new power of this monomial, and that's why this appears here. And then the other entries you can check on your own. They're going to be the same. exactly the same. They're going to be the corresponding edge divided by this. All right.
But for this sum to be converted, we need this to be absolute value of 1 and 1.
Yes. So that was something I was hoping you wouldn't catch, but yes, good. Yes, exactly, right? So if you actually want this to converge, you need this product to be less than 1. Which in some applications, it makes sense because you don't want this to blow up in a sense. So you want this to converge. If you go many times, then you want these lambdas to this effect to go to 0 so that the total effect actually converges. So, well, that is true in the sense that, well, to have this equality in the end, I need that condition. But, well, then to have this equality, I also need some kind of condition, right, on lambda to think about this as an actual convergence series. But what I'm saying is, so while that is true, what is a fact is that this is true. So then I don't need, the only thing that I need, that's actually now a good point. Now that you mention it, I like to now, what is RD reg in this case? Right, so RD reg, it was, by definition, it was all, now in this case, all the lambdas. So maybe let me write them explicitly because our lambdas are now lambda 1, 2, lambda 0, 0, 0, lambda 2, 3, lambda 3, 1, 0, 0. So all lambdas, yeah, that's, I guess I shouldn't have written it like that, but okay. Lambda d such that the determinant of identity minus lambda is not 0. And what is that? So in this case, you have the determinant of 1 minus lambda. And, well, minus lambda 1, 2, 0, minus lambda 2, 3, minus lambda 3, 1, 0, 0. If you take the determinant of this matrix, if you do just expansion, all the possible terms, out of the 6 terms, 4 vanish, right? So only the 1 appears, and there is the 1 corresponding to lambda 1, 2, lambda 2, 3, lambda 3, 1 with a minus. And so okay, I shouldn't write equality here when this is not an equality, but this equality, this determinant is this from 0. Right, so now we actually see a difference between RD reg and RD, right? So now these are actually different. And the only difference is that you require that this quantity is different from 0. And so that is important for us, right? So maybe this less than 1, larger than 1, it's not such an important thing algebraically, but this is important that you don't divide by 0 here. And that is thanks to this condition of being in R reg. Okay. Very good. So this is great. So this allows us to understand identity minus lambda inverse, but actually we will really like to understand sigma itself, right? So how about sigma ij? Can we understand that? And I already raised the example, but well, I hope you have it, right? So I said there are all these summands that appear with the omegas. How can we interpret those? Well, everything just comes from understanding what is sigma ij. It's going to be a sum of where there are products of 3 things, right? So on the one hand, we have some entry ik. There is the entry from the omega. And then there is the entry again from identity minus lambda inverse kj, right? So it's like sums of this form, right? So sums of these kind of products. And so, well, omega kk is easy. This is just omega k. And this, well, this one is easy because we know what this is. This is just a path from k to j. And this, it's transposed. So this is really a path from k to I, which I'm going to write like this. And so the way we should think about the entries of a sigma ij is that we concatenate paths that go from I to some k, but then we come back. And well, come back down, that's what I mean, come back down to j. And this is the concept of a trek that briefly introduced in the tutorial. And so let's define that, right? So let ij in V a trek between I and j is a pair of directed paths so I'm gonna denote it by tau pi I comma pi j with same starting vertex P and such that pi I ends at I and pi j ends at j. And this T here is called the top of the trek. Okay, so trek. Okay. So now Canary is here. And now we can write down the formula for sigma ij. So this is called the trek rule. You'll find it like that in the literature. So the trek rule says the following: sigma ij can be written as the sum over all the treks tau in Tij. Okay, let me here already write. Tij is what you expect. Tij is the set of all treks from I to j. Well, between I and j. Say tau is the trek between I and j. And so a trek is gonna be of this form, right? There's T. Here it's I. Here is j. And so how, once we have a trek such a tau, what is the entry? The entry is gonna contribute at the top. That's the omega that we choose, the entry in the omega. So there should be here omega top of tau. And then it's just multiplying the monomials from each of these. All right. So this would be lambda pi I times lambda pi j. Okay. So that multiplies everything that's along this trek. And that gives us this, this formula. Okay. So does that make sense? Right. So the top is this T, that is the common starting point. And now, now we have a combinatorial interpretation for the entries of sigma. And so maybe we just do one example. Let's see. So we have in this one, so I'm just gonna compute one entry. Let's say I'm gonna do sigma 1, 4. So sigma 1, 4. Here it's important to note, by the way. So here t equals I or t equals j is allowed. So you are allowed to have empty left side or empty right side. So just a directed path would also work. And this is the first entry that appears here. Would be omega 2 lambda 2 4 is the first monomial that appears. And this is corresponding to just the directed path 2 to 4. But now I also have the one omega 1 times lambda 1 2, lambda 1 3, lambda 3 4. This corresponds to the track that, so we need to connect 1 to 4. And 1 is the top here. Sorry, 1 to 4. This should be 2 to 4. Sorry, I wanted to compute 2 to 4. 2 to 4. So there's the direct edge, or there's the one that has the top 1. And then here goes 1, 3, 4. Okay, so omega 1, and then lambda 1, 2 from here, lambda 1, 3, lambda 3, 4. And there's one more track. Does anybody see it? Yes, exactly, right? So it's the one that has the 1 here. And then instead of going from 1, 3, 4, I go 1, 2, 4. Right? So the corresponding track is omega 1, lambda 1, 2, lambda 1, 2, which is a square, and lambda 2, 4. Okay, so then this is, if you actually do sigma, compute the sigma for this graph, this will be the entry 2, 4. And then that's how you, you find it. And so again, so just because of time, I'm not gonna write down the full matrix that we had before, but for this path, I wrote down the full entries, right? Well, what was the sigma 3, 3? If you have your notes there, you will see that this was omega 1, lambda 2, lambda 1, 2 squared, lambda 2, 3 squared, plus omega 2, lambda 2, 3 squared, plus omega 3. But now we can actually understand why these things appear, right? So omega 3 is just corresponding to the empty track, just stay there at 3. This one corresponds to going 2 to 3, 2 to 3. Look that you are allowed to repeat directed paths. That's not a problem.
This is for the
For this graph. For this graph, yeah. Sorry, I wanted to go back to the first example I was writing, and that's for G equals this. And so here, this one will be 1 goes to 2 goes to 3, 1 goes to 2 goes to 3. And so that's why the squares appear. Does that make sense? Okay. So this also means that when you are, it saves you time, right? If you want to write, you can actually compute a particular entry without needing to compute the whole inversion and multiplication. And for writing down the parameterization, then you have control over what's happening. All right, so in the last part, I want to talk about identifiability because that was one of the, yeah.
When we are writing this vector, how can we make sure that we are like have written all of them and we are not missing?
Is there a, sorry?
Is there a tool or a way that ensures us like now we have all the vectors here?
Well, I think most of the time is just practice to see. I mean, what you can do is like you can check for each possible top, right? How many paths are there? So like here is the top with top 3, top 2, and top 1, right? And so you can look at that through different tops, and you can look at directed paths first, and then once you exhaust the directed paths, then you can go. I mean, you can try to order things, right? At first, I'm gonna go like this. I'm gonna go by length, for example, and so here that's I don't know which one. Here, right? So then here first, I would like okay, first the short one here and the long one here, and then yeah. But I don't know. It's not. I mean, if you're doing it by hand, then you have to be. I would double check to see if you got it. But a priori, it's not so easy, right? To just know how many terms there are. Okay, so let me talk about identifiability because this was one of the other words in the title for this mini course. And so, right, we already know what the linear Gaussian graphical models are, and there was something called algebraic identifiability. So what does this mean? This is easy now with my notation because remember this phi g. So identifiability is important in statistics because the idea is that now you're going to have data and you're going to estimate a sigma, right? And let's say we have this graph and we have sigma, but what we actually want to learn are the parameters, right? So what is the influence from 1 to 2? What is this lambda 1, 2? Right? So the equation is, I'm going to give a sigma here, right? So given a sigma in mg, can we recover lambda and omega? That is the question. Okay? And so in mathematical terms, this is easy to state because it just means that phi g is injected. Is phi g injected? And so this leads to my following definition. So in general, for a parameterized model, I'm going to write theta m parameterized model. We say the parameters theta are identifiable. Okay, I guess I do want to say parameter singular. Parameter theta is identifiable. Sorry, just gonna say parameter theta is. And then I'm gonna tell you different kinds of identifiability. So, okay. First option, globally identifiable. If and only if the phi is injected. So that's the best case, which just means that this map is injective. So that means if I give you a sigma in this model, you are able to recover uniquely the lambda and the omega. But okay, not always this is possible. So we have then the generically identifiable. So that's the next best case. And generically identifiable just means that this the images are generically just 1 point. So this I'm gonna write like this: phi inverse of phi of theta is just theta for almost all theta. And so, okay, what do I mean by almost all? So do you know the concept, are you seeing the concept of generic in algebraic geometry, right? So when you say that something holds generically, usually you mean it holds outside, or it holds in a Zariski open, non-empty Zariski open set. So this is what we mean here. So that means that for almost all theta, and I'm going to say almost all because if I were to put some probability measure, right, on this space of thetas, then this will happen in probability 1 if I just choose one randomly, right? So that's what I mean. So there may be some lower dimensional subset where this thing is not injective, but normally it is. And finally, algebraically identifiable. And remember, that was actually the title from the course, algebraically identifiable. If and only if, well, now maybe we don't get this uniqueness, but the next best thing is that this is finite. And again, for almost all theta. So algebraically identifiable means that the fibers are generically finite. So maybe we don't have a unique parameter that we can go back to, but if there are finitely many, you can still try to find one and just go through them and then maybe choose the one that that is best. And that's why we call it algebraically identifiable, because usually, I mean, if in the context of these algebraic maps, the preimage you're gonna have to find there will be a polynomial equation of certain degree, and this degree is gonna be the number, right? This fiber, this degree of the map. All right, so let's look at an example. Okay, let's do a very simple example. Just the graph that goes from 1 to 2. So then the phi, which now everybody can compute thanks to the track rule, but I'm just gonna write it here for you. So this should be omega 1, lambda 1, 2, omega 1. It's symmetric, so of course this is here. And lambda 1, 2 squared omega 1 plus omega 2. This is coming from the two tracks, the empty track and the one that goes from 1, 2, 1, 2. And so given sigma, and sigma is going to be sigma 1, 1, sigma 1, 2, sigma 1, 2, sigma 2, 2. The question is, so recover lambda 1, 2, omega 1, and omega 2, right? So that's what we want. So we would need to solve a system of polynomial equations. So that's when the algebraic tools that you know come in handy. In this case, you can do this by Gröbner basis, right? But in our particular case, this is easy enough that we can just solve directly, right? So the sigmas are given the omegas you don't know and the lambdas you don't know. So you need to just find them in terms of the sigmas. But then you can see that this is easy because, for example, omega 1 is automatically sigma 1, 1. And once you have that, then you can get lambda 1, 2 by just doing sigma 1, 2 over sigma 1, 1. Right? And then the last one would be omega 2. How do you get omega 2? Well, you subtract sigma 2, 2 minus, sorry? Yes, exactly. So then let me write then everything in the same denominator. So I'm just gonna write, what I want, I have my, yes. Let me write like this. Sigma 1, 1, sigma 2, 2 minus sigma 1, 2 squared divided by sigma 1, 1. I guess that's what I wanted. You agree? Yeah. Yes? Great. I wanted to write it like this because I wanted to see how being sigma positive definite, right, which is the meaning the model, everything comes here, right? The omega should be positive, and it is, and this should be positive, and it is, because this is actually the determinant of that sigma, right? Which is again positive because it's positive definite. And so yeah, so you can see this is actually a rational expression in terms of the sigmas. And so that's why sometimes this generic identifiability is also called rational identifiability in the context of polynomial maps. So I'm gonna run rationally identifiable. Right? Because there is a rational expression. And so yeah, this is an example of globally identifiable. Okay, so this was the example, and I'm running out of time, so I'll just gonna write one more example here quickly, which is 1 goes to 2, 2 goes to 1. This one, you can check that this will be not identifiable. And this should be intuitive because there are just too many parameters. If you think about it, how many parameters are there? There is omega 1, omega 2, lambda 1, 2, and lambda 2, 1. So there are 4, if you think about the system of equations, there are 4 unknowns, but you only have 3 equations because there is this symmetry in sigma, right? So if you have this equal to sigma 1, 1, the other one equal to sigma 1, 2, and the other one, so sigma 1, 1, sigma 1, 2, sigma 2, 2, only 3 equations, then you'll see that this is not possible. You will only be able to solve this. All the fibers are going to be infinite. And so you're in the not identifiable case. And then to end, I will leave you this as an exercise. What happens if you have this larger cycle? Because now there are 6 parameters, right? Namely, omega 1, omega 2, omega 3, and lambda 1, 2, lambda 2, 3, lambda 3, 1. But you also have 6 equations, right? Because coming from sigma 1, 1, sigma 1, 2, sigma 1, 3, sigma 2, 2, sigma 2, 3, and sigma 3, 3. And so now this has a chance of being identifiable. And well, I'm maybe not going to spoil it for you. I let you do it. But this is not globally identifiable, but it's generically, it's algebraically identifiable. It's not generically identifiable, but it's algebraically identifiable. And I'll let you compute what is this cardinality of the fiber for a generic point here. You can do it by examples. You can put some sigmas and try to solve. You can use it either by hand or using maybe some computer algebra software, grammar basis. Okay, so I will stop there. Thank you.
So are there any questions from the audience? So, IB Karachi, are there any questions from your side?
No, no.
No, okay.
I
Okay.
think there is a question here.
Yeah, there are some.
When you apply this to actual data, it seems very computationally expensive.
Well, yes, depends on the size of your graph. But yeah, it is. I will say, yeah, it is a bit expensive because you need to solve this system. But I guess one good thing is that, I mean, if you once you don't need to solve it once, right? So once you solve it once, then you can do it for a lot of data, right? So you have a model in mind. Let's say this one. Maybe this one is a bit crazy, but yeah, okay. Let's say this one, and then you have your data. You only need to solve these things once, and once you store them, then you just need to substitute, right? Like here, the data may be different. You will have different values for sigmas, but then you can reuse. And so that's when it's useful. If you want to go through many models with the same data, then that's when it gets expensive. That's true.
Okay, yeah.
Just trying to understand kind of the usefulness of
Mhm.
having this equation. So does this help us? You use this to calculate covariance, and it will be cheaper than absolutely calculate covariance?
Yes, in one way. I mean, at some point, this can be also be made combinatorially, explode. But I guess so. This gives us a nice, it helps us for understanding, like more for theoretical properties, right? So one of the things you can see is like, if there is a unique trick between two nodes, for example, then this becomes a monomial parameterization, and then automatically we know we have a toric ideal, right? Or if Tij is empty between two nodes, then you know this entry is 0 without needing to compute the whole, the whole parameterization, the whole multiplication stuff. So we have one example, right, with the 1 and 2 pointing to 3, where the entry 1, 2 was 0, and we did it by actually writing everything out. But now we can already know because there's just no track between 1 and 2 in that case. So then automatically 0. So yeah, it's helpful in this way.
There are general class of graphs for which phi is always injected.
Oh, that is a great question, and we're gonna look at that next lecture. Yes.
Okay, if this is the case, let us thank the speaker once again. Now we have a tea break and coffee break for 30 minutes. At 11 sharp, we have to be assembled once again in the same room for the third lecture of Miruna. And today we have two new speaker, Cordy and Rainer, will be starting his course today. And Aida Miraj is also the one, a new speaker of the day. So she is going to start her course. So there are two lectures by Aida. So one by Cordian in this on this day. Okay, have a great day.